My name is Bryan Boreham. I work for a company called Weaveworks. I work in Shoreditch near here. We make tooling for people building applications using containers. I decided to talk about what might be a slightly controversial topic, but the actor model. So who knows all about the actor model? Yeah, I thought, yeah, you guys came to heckle, right? Well, I encourage you to heckle, actually. There's no room for questions at the end, so if I say something you passionately disagree with, then, come up and beat me about the head, because that's the only way you'll get your point over. Or you could tweet to me at bboreham, which is my cunningly constructed Twitter handle. Okay, so I'm going to do a talk. We need all the cat memes, right? So I do not recommend you go to Google image search and type in actor model. Because you get this is the award for the greatest actor / model in the world. But an alternative formalism is found in Wikipedia. So it's a mathematical model of concurrent computation that treats actors as the universal primitives of concurrent computation. So we had to say concurrent computation twice there to get the point across. That's great. Okay, so we're all clear now? No? Oh well. So what do people say about actors? That they're good for concurrent systems. Yeah, we're hearing that. They're easier to write, easier to reason about. Well, is that true? So this is me, effectively. I have been learning about actors, and I don't claim to know everything. And I'm going to tell you kind of what I found on a certain journey. Okay, let's go back there. Okay, I don't know what's happening here. There you go. Yeah, exciting effects. Yeah, I have some predictions about reactions to this talk, but I've put them in a sealed envelope at the end of the talk, so we'll get to those. So I joined this company, Weaveworks, 2 years ago, and their first product was a software network for containers. And the guys that set up Weaveworks came from RabbitMQ originally. Rabbit is written in Erlang. Erlang is a highly actor-oriented kind of thing. And so they'd written this SDN in Go using actors. The whole program was full of actors. They had actors for connections, for peers on the network. It's a peer-to-peer network. They had actors all over the place. So that's kind of what began my journey. I'd never really considered actors before that, and I got to read a lot of them. So let's take an example, a kind of motivating example for the usage. Within the Weave network, there's this thing called a connection maker, and basic idea. Yes. Okay. So the basic idea is that you tell it you'd like it to make some connections. It builds up a list of the connections you'd like it to make. It goes out on the underlying network and tries to find those things that you're trying to connect to. Hopefully it finds some of them, and it makes a solid connection to those ones that it does find. Some of the things that it's trying to connect to may be unavailable. That's kind of one of the features of the thing, that it can be resilient to nodes coming and going. So it will carry on trying to make those connections and eventually time them out. And or in fact, their TCP dial operation will time out. And it moves those into another bucket. It says, these are ones I'm going to retry later. Runs a little timer, waits for a certain amount of time, and then essentially goes back to the start again, and it has a list of things it's trying to connect to, and it just sits there repeatedly over time trying to make connections. So the properties of this object we want it to be async. We don't want the whole rest of the program to halt while it's going about its business of trying to make connections. The connection attempts, because they're a TCP dial operation, are synchronous on one Go routine. And we also have timer-driven events. We have a timer running that kind of drives retries. And those things together, I guess that's part of my argument, that kind of combination of things gets complicated if you try and code this up with mutexes, because you're going to have things coming in on some Go routines trying to lock things. You're going to have like some kind of loop running with a timer, some other Go routines running those TCP dial operations, and you don't want to hold the lock while you're trying to do a dial operation because it's going to hold it for 30 seconds or something like that. That's no use. So I think that's part of the kind of the motivation to seek a different way to do things. That it would get a little bit complicated trying to code this up using mutexes. So what is an actor? This is we said at the beginning it's a mathematical model. It was created, the model was written up in the first place in 1973. At that time, people, they're just kind of moving out of the time when you toggled in the program in binary. People were seeking for models. The other model you may well know about, communicating sequential processes, the CSP that really Go is much more based on. It's in the name. It's fundamentally sequential processes, and then they do some communicating. Actor is a fundamentally concurrent model. And the basic idea is that there's a thing running, which is the circle, and it's doing stuff, and it has a mailbox where messages arrive. And everything that it does is done in response to a message. Concurrency is achieved by having lots of actors, or however many you want. Each actor has its own mailbox, and actors send messages to each other. It's actually a very simple theory. It's quite cool that people manage to write PhDs and great treatises on how this stuff pans out. So, okay, take that model. How does that translate into Go? Well, it's very simple. An actor can be implemented in Go as a struct plus a Go routine. So the Go routine is the thing that's going to process the messages. The mailbox where the messages arrive can be implemented as a chan. Okay? It's very simple. Here's the code. So let's walk through this. I have a laser gun. Hey. So in order to start off an actor, we make a chan. We construct our struct with whatever it needs in it. We fire off a Go routine, and then we give it back to whoever asked for it. When we want the actor to do something, we send a message on the chan. And the Go routine is going to run this loop. And the loop reads from the chan. And whenever it reads something in, it deals with it. And then it goes back around the loop. So who's feeling cheated? Well, there's a couple of things to think about. First of all, what are these things in the chan that we send in here? And secondly, how big is the chan? Those turn out to be key questions. So in terms of my journey learning about this stuff, when I came to this code base at Weaveworks, the things that we sent in the chan, essentially the type of message was encoded as an int. And then there was stuff in a struct that was the kind of the payload of the message. So inside that loop there was a switch. We kind of unpacked the message and we looked at the enum, we switched on the enum and we unpacked the stuff that was in the struct and we went about our business. That was a little painful to deal with because every time you wanted to add a new kind of message, you kind of had to add it in multiple places. You had to add the enum, you had to add the sending, you had to add the struct that it was, So I worked with that for a bit, and then I came up with a better way of doing it. I don't claim to have invented this. I mean, I think I thought of it myself, but I'm not the only person to have thought of this. So what we actually do now, the thing that we send on the chan is a func. So this is very close to the real code inside the network. When you want to add an address that we want to try and connect to, we receive the address, which is going to be something like a DNS name or an IP dotted name, something like that. And this is a little closure here that captures the address. And we send this entire function on the chan. This is really cool. We still have that loop. Well, let's look at the loop. The loop pulls things off the chan and executes them. And we also have the timer going on. I just wanted to kind of indicate how that works. But this is like beautifully simple. And it fixes that problem of when you want to add something, you need to add it in multiple places. Because I'll just go back a slide. If you want to add an extra kind of a message, you just do it exactly like that. You put the whole body. So I think we lose one indentation. My boss is pretty passionate about not indenting code more than you have to. So he was a little sad about that, but that's it, right? So that is the fundamentals of how we in the Weave network do things in what I'd probably describe as an actor style. Let's just extend that theory. What if you had a thing where you need to make a call? Actually, let's just sort of maybe I missed out a couple of things. There's no locks in this code. I can have lots of these things. In fact, we only have one connection maker in the network, but we have lots of connections, and they run as actors as well. And we never have to lock our data structure because we're pulling these things off the queue one at a time and executing them. So inside the action, inside the loop, things run completely single-threaded on one Go routine. And they run asynchronously. So this function will return immediately as far as the caller is concerned. this will run on one Go routine, and then the actual bit inside the braces will run on the actor Go routine. And because we only run things one at a time inside that loop, we never have to lock and unlock the data that we're manipulating that is owned by the actor. So that is a crucial property of this way of working. Okay, so this is a thing that is completely asynchronous. You just want to add the address and tell it to get on with it. What if we want to ask something back from the actor? That's the loop we saw before. So there's an example where we basically get a string value out of our connection maker, which consists of the status, so just of some effectively debugging information about how it's doing. So in order to do that, we make another chan, which is going to hold our return value. The actual implementation I've sort of hidden just for the sake of exposition here. But once we have that value, we send it back on the result chan, and then the calling function waits until it can receive a function on that chan. So every time we call this function, we create a new chan, which is just used once to pick off the return value, and that's how we do that. That's how we have functions which are synchronous with respect to the caller. That in this case it's calling in and asking a question, and then it's going to get some answer. Okay. Okay, something I mentioned earlier. How big should the chan, the mailbox that we're using for our actor, be? I don't know. Should we have a vote? Oh. Peter's voting yes. Well, let's go through what are the implications of the different choices. If we make that chan 0, then 0 means the sender and the receiver synchronize. The sender can't proceed until the receiver receives, and vice versa. And that's really not very good for concurrency. We said at the beginning the actor model is all about concurrency. So we have to vote no on 0 as a choice. We can knock off the one at the end as well, because Go does not allow unbounded channels. This is a source of great sadness to Erlang programmers. Erlang does have unbounded channels, and that's a source of much wailing and personal anxiety in certain quarters. But it is what it is. Rob Pike decided that you can't have unbounded channels, and I doubt if you have that much memory anyway. So. So two choices down. This is like Who Wants to Be a Millionaire, right? We've 50-50. We've eliminated 2 choices. There's 2 left. So the reality is, in practical terms, that it shouldn't matter. In practical terms, you should be able to run these systems with a channel size of 1. You'll be able to get one thing kind of teed up, ready to go in asynchronously, and then if anyone else came along and wanted to do something, they would block, because the chan would be full at that point. Now, for that reason, we in practical terms we run with an n of 16. This is chosen somewhat pragmatically. Well, to be fair, we run our unit tests with a channel size of 1 because it's more likely to throw up mistakes in the logic and the threading. But a bigger channel size, it gives you one nice property, which is that messages are executed in the order that people arrive, because they go into the queue in that order, and they'll be pulled off the queue in that order. Once the queue is full, once you're up to the size of the chan, everybody blocks. Everybody. So if you take our number of 16, if you happen to get 17 people trying to make a connection at once, 17, 18, 19, all those extra ones after 16 would all block. And then once the chan empties a little bit, it's non-deterministic which one runs next. It's a kind of a nice property to have, that most of the time things will execute in the order they arrived. Yeah, so the answer to this question is either 1 or n, depending on how you're feeling. For larger n may give you a slightly nicer property. Okay, so what if you didn't want the sender to block? What if in the semantics of your program, it was more important that you carried on doing stuff than that you waited for that message to be delivered, because we don't have unbounded channels. So Go lets us do this. Go lets us select on the sending side, and we can, in this case, if there is room in the channel, then we get it in there. If there's no room in the channel, we fall to the default case on the select. In my code here, I'm throwing it away. Maybe I log an error. Maybe you can. In fact, we have a sort of a gossip peer-to-peer information passing system within the Weave network, and we actually do a more sophisticated thing, which is we try and merge successive bits of information. If we know how to do that, we try and combine them up, because that gives a nicer property under load that we recover faster. The basic principle that Go lets you do a select on the input to a chan, and it'll either work if it can or do the other thing if it can't. Okay? Okay, we're getting to the home straight. So some more things cut and pasted from the Wikipedia page on the actor model. An actor can designate the behavior to be used for the next message it receives. Never needed that. Like, you could have some, in your loop, you could have some state, some sort of select switch on, I don't know. Never needed that behavior. I think that comes from people thinking in terms of state machines and kind of wanting to switch out one state machine, switch in another state machine. So we never needed that. Messages are sent to actors at addresses. And if you want to go kind of depending on the theory, the CSP thing is processes are anonymous and channels are named. In actors, the thing you're sending it to is the identity, is the thing you know about, and you don't know anything about the channel. You don't know anything about the mailbox in the actor model. In our Go code, obviously, we're just using a pointer to this struct as our address. So that's very simple. But it gives you quite a nice property. In fact, I was having a chat at the social event about people who wanted to name their Go routines. This is not naming Go routines, but by sort of associating one struct with one Go routine as our fundamental model, the actor model, we've given our Go routine an identity. In terms of debugging and logging and things like that, we always know the identity of the struct that we're in a method of, so we can use that. We do that in all of our logging, and I didn't really think about that until I was involved in this conversation over a beer. Oh yeah, the bottom one, unbounded non-determinism. That sounds good, doesn't it? That's do we want that? So that phrase comes from a spat between Hewitt, who invented the actor model, and Dijkstra, who liked having spats. And this kind of goes back to the infinite length channel. If you have infinite length channels, then the system has the property that a message can be delayed forever, but still retaining the guarantee that it will be delivered. And Dijkstra said that's BS. Like, what use is that? So Dijkstra's model goes with the property that that you may not be able to do something you wanted to, and the guarantee is that you will either be able to do the thing you wanted to do or fail. And I'm kind of with Dijkstra on that. Sounds more like the programs I know. In practice, again, this is my journey. This is what I found along the way. So there's no locks and unlocks. That's nice in the code. And I should say, I'd been with the company a few months, and I was asked to write a new thing, which was the IP address manager within the network. And I started off. I wrote that whole thing with no actors. It's like, what is this actor stuff? I don't like this. That was me a year and a half ago. And I just got so tied up with all the locks I was putting in, and I had like multiple structures and multiple locks, and when do I have to do them with a hierarchy, and I scrubbed all that, and I rewrote the thing in the actor model, and that's what's running today. I mean, I was entirely happy with that change. I know. Well, anyway, that's the way it came out for me. It is a simple model. It simplifies the code that you're writing. I mentioned the identifying the Go routines a minute ago. On the con side, the fact that your code is always running on a different Go routine can be kind of irritating. In terms of debugging and figuring out, you can't just sort of step through a method because it's always going to call off to a different Go routine. Unit tests is another case where you kind of have to fire up that extra actor loop and take care to respect its properties even when running your unit tests. That's kind of annoying. It does enforce a single thread of control for each actor. You can't do a sort of multiple reader, single writer model in this way. And a little joke I put under con, there's no framework. I don't get to publish a library, the actor library for Go, because it's only like 4 lines of code. So I'm sad about that. Sorry, that's me. So one of the good things, with no locks, there's no deadlocks, right? No? There's a couple of people doubt that statement. Yeah, you do get deadlocks. This is pretty much the real. Well, it's a simplified version. I ended up drawing out this diagram at a particular point where our system had completely locked up in production. Where's my laser? They shouldn't let me have lasers. So basically there were these. There are 2 actors here, and there's the chan for each actor, and when both those chans filled up, everything stopped. That's the short version of that. That took me like a day and a half to find. We've also had even more exciting instances of this because it's a distributed system where you get a deadlock across multiple machines. We managed to fill not only the actor chans but the TCP buffers as well. Just with great power comes great responsibility or something. Yeah, it's not. It doesn't fix every problem in concurrency. So I said, here are my predictions. What do I think at the beginning when I wrote this talk? How do I think people are going to react to this? So I think a lot of people are going to say, just come off it, just use a mutex. All this actor stuff is just fancy nonsense. But my guess is actually, let's do a show of hands. Who's thinking this is, well, don't bother, just use a mutex. You can be honest, I don't mind. Half my colleagues, well, actually 3/4 of my colleagues say that. So, okay, no one's owning up to that position. But I'm reasonably confident a lot of you are thinking, well, that's what I do anyway. All you did was give it a fancy name. So does anyone feel that way? One person? Yeah, people feel that way. Yeah, okay, great. So I figure if I can annoy each half of the audience equally in the opposite direction, then I've completely succeeded. So you know, a few takeaways that I just remind you of this useful phrase from Effective Go: share memory by communicating. You know, it's really, Go has fantastic facilities for communicating between parts of your program. So do think about using them. You can work in an actor style. I'd probably call it. You know, it's just a bit of code in Go. There's no framework. I can't get those stars on GitHub, which are as good as money, right? It departs from the actor theory in a few ways. I'm like, well, the more you know about the theory, the more ways you could spot. But I personally don't care if it gets the job done. We have had this code in production for 2 years, and we broke out the gossip, the peer-to-peer part as its own library. That is reusable if you can both take a look at the way we use actors, and you may want to use a library for constructing peer-to-peer systems of any kind. So there we are. Thank you very much.